Hi everyone. Um, this is the example problem that I'm adding for this Monday's class, and I want you to do this example before example number 20 on page 229. So the question is about a 50-pound block, and it is released from rest at the top of a lubricated ramp that is 10 feet long. As the block slides down the ramp, a resistive force F is already shown on the figure of 15 pounds is applied to the block to keep it from moving too fast. And there's several things I want to find out. Part A and B is using conservation of energy. We will determine the speed of the block when it reaches to the bottom of the ramp. Part A is with the force applied F, and part B is without it. And part C and D's are same thing, repeats of A and B, but using another method, and that would be Newton's second law. So I've already shown several things here to save some time, but and I'm gonna highlight those when we're solving. But again, some free body diagram, and I will draw this later again. So just want to think about like what are the forces that are acting on, whether they're constant or not. So I just want to see the forces. And the motions, I also thought about that. So it's going down the incline again along the x direction that I stated here. And that is the displacement, because we need to figure out some work done, and we will need to think about displacement as well. So one thing is which is different, and it may look weird, is that I have an x-axis and a y-axis. They are not really the same coordinate system. Okay, so I'm gonna do one thing and then change it to another thing when I do my solution. So I'll explain what I mean by that. So in this example, I really want you to understand how to apply conservation of energy, and we are going to do a very different way of doing this, applying energy conservation, especially if you look at Wiley. They're just like saying, okay, delta K plus delta is equal to 0 or something. Instead of giving specific things, we are going to start with a general equation, and then we are going to eliminate things and get our specific equation, whatever it is. Okay, so we are not going to rely on the memorization. We just need to understand the procedure, and I'm going to try to explain that in this video. Okay, so assumptions are frictionless, it's 1D motion, and it's constant force because it has 15 pounds. That's kind of why we can also solve this problem in another way by using second law, Newton's second law, and also the constant acceleration of motions. And that's the part for C and D. I'm not going to show the solution on the video, but the written form has the solution for all of those parts. So estimation, since we are slowing it down by applying that force F, we expect that it shouldn't really move more than a few feet per second, right? And but for part B and D, where the F is no longer there, it should be greater than part A and C. And A and C should be the same, B and D should be the same. Okay, so how do we solve energy conservation equation problems? So part A, we are going to find the speed at the end of the ramp. So I'm going to say part A. So first thing you do, the step one, is really kind of writing the equation. So the equation would be delta K plus delta U plus delta I. All the energies, K is kinetic, U is potential, I is internal energy. And delta I is going to be 0 for a while, but later we will use that as well. On the right side, we are writing not the energies, but the way that we can add or take away some energy from the system. Okay, so those are the work. Work is related to the energy that way, and also heat, Q. Okay, So this is how we're going to use the energy conservation equation for a while. It's a little different than the equation sheet. In the equation sheet, the kinetic energy is split, potential energy is split, and also internal energy is split. Now we're not splitting them, okay, because we don't know much about them yet. We're just starting, so we're putting them all together this way. And the next thing is to simplify this. So you can either put these into your assumption, or you can now think about which ones are zero. Do I have kinetic? I should keep this term because I'm thinking about velocity, and kinetic is 1/2 mv squared, so there's velocity square in there. So I'm gonna keep the kinetic term. Is there a change in elevation? Okay, so that's what you think in terms of potential energy change, delta U. If there's a change in elevation from initial to final, then you have to keep that term too. Is there change in internal energy? Internal energy is related to the molecular level, so is there a change in the temperature or a change in the pressure? The answer is no, so we're going to say no. And let's explain why. No change at temperature or pressure, T or P, okay? So those are the things that we're going to write them down like this, and I really want you to make a habit of doing that as well. And then the work done. Do we have work done? If you look at the free body diagram, we have three forces. So what we do usually when we apply energy conservation, we skip work done. Okay, but we will do that later. Let's just simplify the equation. So I'm going to skip work term, and I'm going to look into it later and more carefully. So the heat is also zero because, again, we can just simply say no heat added or taken away from the system. Okay, so after this, we end up with the equation. There are three terms left. Delta K plus delta U equals to work done. Okay, so now it's time to look into the work done more carefully. To be able to do that, we need to think about our free body diagram again. Okay, so I'm going to draw the free body diagram on the side. We have the object going down the incline like this. And we have the applied force, something like this. So hard to draw straight lines. Okay, F, and the weight force downward, and normal force, which is perpendicular to the surface. So remember that x-axis that we chose is down the incline, so it's something like that.